Okay, so double replacement reactions. This is going to involve two compounds this time. Unlike single replacement reaction, which was an element in the compound, this is going to be two compounds. So let me just kind of give you the form of it. We're going to have, let's say, a compound AX, just hypothetical compound. A would be our positive, X would be our negative. And then I combine that with BY. Again, hypothetical, not real elements, just B being positive, Y being negative. When they come together, they're just going to trade partners so that the A is now paired up with Y, so it's still positive with negative, and the B is going to be paired up with X. Right? Now, it's very simple process. Let's take a look at a real example, rather than just sort of the format. Let's say instead of AX I have Ki, so potassium iodide. Now the physical states here are important. Ki is going to be aqueous, and then the By, let's replace that with lead 2 nitrate. So PbNO3 also aqueous. The reactants in a double replacement reaction are pretty much always going to both be aqueous. Alright? Now let's take a look at what happens when they sort of trade partners. In other words, up here A and B traded places because they were both the cations. And here we can say K and Pb are going to trade places. So on the product side, I'm going to get K paired with nitrate, or potassium nitrate, and I'm going to get lead 2, and I know it's lead 2 because of the 2 on the nitrate over on the left, so it would still be lead 2 on the right. So lead 2 is going to be paired with iodide, which would mean PbI2. Okay? Now there's a really important point that we have to make here before we go any further, and that is that with our two products here, one of them has to be an insoluble solid. So one product must be insoluble, and essentially we mean, if you remember a word from last time, we mean that it must be a precipitate. For a reaction to occur. So otherwise, if neither would be insoluble, if they're both soluble, if they're both going to end up being aqueous, just like the reactants were, then we haven't done a reaction. Okay? So let's go ahead and take a look here. The way we figure this out is also in the back of your yellow periodic table, and that is your solubility rules, which look like this. So what we do is we go through and we look at the solubility rules for each substance. So in the products I have potassium nitrate, and our solubility rules are going to be defined in terms of the negative ion. So all I have to do is find in my solubility rules the rule for nitrates, and it's right there at the very top. It says nitrates, and it just means anything that has NO3 in it. In this case, it's potassium nitrate, but it could be any nitrate, is going to be soluble, which is going to mean aqueous. And there are no exceptions to that. Okay? So what I'm going to do is I'm going to put AQ after potassium nitrate, again, because that's telling us that all nitrates are soluble, and so potassium nitrate is soluble. The next rule we need to look at is the rule for the iodides, because that's what the other substance is. It's lead 2 iodide. So if we go back to our rules, it says for basically halides, meaning halogens that have a negative charge, including iodide, they are going to be soluble, but there are some exceptions, and if you'll notice, lead with a 2+ charge is one of those exceptions. So most iodides, or bromides, or chlorides, or fluorides for that matter, would be soluble and would be aqueous. But lead 2, along with these other two guys, lead 2 is an exception to that, which means it's not going to be soluble. It's not going to be aqueous. So that means it's going to be insoluble, which means that I'm going to put the physical state S for solid next to the PbI2. And that is critical, because if I had not formed this solid precipitate, PbI2, I would have called this a no reaction. Okay? So the last step, of course, is just to balance. And it looks like I need a 2 in front of Ki to balance my I's, and 2 in front of KNO3 to balance both my potassiums and my nitrates. Right? A simple sort of model for this, if we were to kind of draw why is it that we need an insoluble precipitate to form in order for this to be a reaction, is if I just kind of look at a picture of what these would look like. Let's say I have Ki in one beaker. So this is my Ki, and it's aqueous. And what that really means is, let's just symbolize, let's make K these little green guys, so that's K, or K plus I should say, and let's say red are going to be my I, so that's I minus, and these guys are just going to be floating around independent of each other, and the reason that we say that they're independent of each other is because they're aqueous, and so they're dissolved, they're surrounded by water molecules. So that's what a model of an aqueous solution of Ki would look like. Lead 2 nitrate, that is my other reactant, is in this other beaker. Let's change up colors. Let's go with maybe purple for lead, or lead 2 I should say, so Pb2+. It's going to be purple. So one of these guys, maybe 2 of them floating around in there. And then nitrate, well, nitrate's technically a molecule, a charged molecule. It's a polyatomic ion, so it's NO3. So I'm going to draw it, but I'm going to keep it simple. I'm just going to draw it as a little dot. We know it would look a little more complicated than that because it's made up of 4 atoms. But just to keep things simple, I'm going to draw it as a little dot. Now there would be twice as many nitrates floating around as there would be leads, right? Because in the formula there are 2 nitrates for every lead. But anyway, if I put these two together, in a reaction, and in the same beaker, or and I do a reaction, if I get 2 aqueous products as a result, what that would mean, it would mean that these ions, these little greens and reds and purples and blacks, are just floating around still, and so nothing has happened. It's not unless I get a solid insoluble product, like in this case PbI2, that I know that I've had a reaction. So when I do put these together, the little purples, the Pb2 pluses, and the little reds, the I minuses, they're going to come together, and that's going to form, and I guess I should have drawn it all together as a little crystal. That's going to form a little crystal, right, of PbI2. They're going to all kind of clump together like that. And that coming together is what actually makes this a reaction, because if that doesn't happen, then all I'm doing is taking my ions that I had over here on the left and putting them in the same container. If 2 of them don't come together to form a precipitate, then I haven't done anything. Now in this case I am going to have a couple of leftover ions that haven't changed, and that's my KNO3, that's my K plus, which was my green. So I'm going to have still some of my little green guys floating around, and then that's going to be my my NO3 minus, the little black ones, and so they're going to be floating around as well. And so that represents, this represents my precipitate. So that's that, and then these two guys represent my KNO3 aqueous. Okay, let's try maybe two more examples together. We'll pause after each one, see if you can finish it, show the answer, and then move on. So let's go with barium sulfate. And we don't really have to talk or think about what's on the reactant side. We're just always going to assume that it's it is soluble and aqueous, even if the rules tell us that it's not. And then we're going to put that together with, let's go with CuCl2. And I want you to go ahead and see, go ahead and pause here in just a second. I want you to see if you can figure out what products would form in the right side, and then look at your solubility rules in the back of your yellow periodic table to determine whether it's a reaction or not. You can go ahead and predict the products and then decide if it's a reaction, and if it is not a reaction, you can just cross out your products and say NR. So go ahead and pause and give it a shot. Okay, so barium would trade places with copper, so that would be paired up with chloride, and since barium is +2, chloride is -1, I'm going to get BaCl2, and I'm going to get copper to sulfate, and then those are +2 and -2, so I don't have to change any subscripts. So let's see if this is a reaction. Chlorides are down here. They are typically soluble, and barium is not an exception. So barium chloride would be soluble. And then sulfates are also typically soluble, and copper is not an exception. So this is actually going to be aqueous, which means it's a no reaction. So I don't really have to balance it because it's not a reaction that's even going to happen. Alright, so let's try another one. Okay, let's go with sodium sulfide, Na2S. And let's go with silver acetate. So AgC2H3O2. Both of my reactants are aqueous. Go ahead and figure out what would trade places, what would be left with, and if it is a reaction, you can go ahead and predict which one would be insoluble and balance. Okay, so sodium would now be paired up with acetate. If I look at my other product, I'm going to get silver paired up with sulfide, which would be Ag2S, because silver is +1 and sulfide is -2. So sodium acetate, if I look at my rules, acetates are pretty much always soluble, no exceptions. And we could also say sodium at the bottom down here is always soluble, no exceptions. So sodium acetate is definitely aqueous. So if silver sulfide is also aqueous, we have another no reaction. Let's see what happens here. So I'm going to look at my rules again. Sulfides are usually actually insoluble. There are some exceptions, a pretty long list of exceptions, but silver is not one of them. So therefore, silver sulfide follows the normal solubility rule for sulfides, which is that it is insoluble. So this is a solid. And since this is a reaction, I should go ahead and balance it, which is going to mean putting 2 in front of silver acetate and then a 2 in front of sodium acetate. And I'm done. And that's how we predict a double replacement reaction.